Chemistry, this lesson is on formal charge and resonance. So we know that oxygen in its atomic state is a neutral atom with 6 valence electrons. In a chemical bond, oxygen also wants to feel as if it has 6 valence electrons. If it does, then it will feel in its most stable state. So formal charge is a way of determining the configuration of a molecule that will occur in nature. Nature prefers the most stable configuration of a molecule. Let's go ahead and get into an example. We'll see what this means. So the formal charge of an atom is given by the formula. Formal charge equals the number of valence electrons that an atom has in its natural unionized state minus the number of lone pairs it has in its bonded state minus half of the bonding electrons in its bonded state. So it sounds like a confusing formula. Let's see some examples and we'll see how it works. So example, both of the following configurations can be formed using the rules for covalent bonds. So there are two formulas for carbon dioxide. Now the one on the left is the one that's preferred in nature. It's the one that's actually made in nature. But the one on the right also meets the rules for making a covalent bond for carbon dioxide. So how do we know that the one on the left is the one that's preferred? So let's go ahead and do this example. So the way you would take the formal charges, let's look at oxygen. Oxygen naturally has 6 valence electrons when it's not bonding. In this particular bond, if you see the 2 lone pair electrons on top and bottom of oxygen, they belong to oxygen. So that's 4 electrons that belong to oxygen. In addition, the 2 bonding pairs, the 4 bonding electrons in between oxygen and carbon, we say that half of those belong to oxygen and half of those belong to carbon. So if you take the 6 that oxygen naturally has in its unbonded state, and in this particular bond you subtract the 4 lone pair electrons, not lone pairs, but lone pair electrons, and then subtract half of the bonding electrons, that should give us 0. What that means is in this bond, the 4 and half of the 4, which is 2, should be equal to the number of electrons that oxygen naturally feels. So we see that that does turn out to be 0. So oxygen feels very comfortable with this type of electron arrangement. So oxygen has 6 valence electrons. Now the oxygen in this particular bond has 4 lone pair electrons. And you take half of the bonding electrons, that's 2, and if you subtract those out, you get 0. So now we're going to take the formal charge for carbon. Naturally, carbon has 4 valence electrons. In this particular bond that you see in the red box, it doesn't have any lone pairs, but it has 8 bonding electrons, so you say that half of those belong to carbon and the other half belong to each of the 2 oxygens. So if you subtract those out, you get 0. So carbon has 4 valence electrons. Carbon has no lone pairs. We take half of the bonding electrons, we subtract those out, and we get 0. Now if we take the other oxygen, it's the same as the first one. 6 valence electrons for oxygen in its natural atomic state, minus 4 that are lone pair electrons in this bond, minus half of the 4 bonding electrons, and that gives you 0. Okay, so if you look at those 3 in total, you have everyone has 0 for a formal charge. That is a very stable configuration. In fact, that's as stable as it can have. So the formal charge of 0 on all elements means that this configuration of CO2 is stable. Okay, here we go. Let's do the one on the right. Now that oxygen, again, has 6 valence electrons in its natural state. You see here it has 6 lone pair electrons, if you count all of the lone pair electrons there, and then it has 2 bonding electrons, so you take half of that. So 6 minus 1/2 of those 2 bonding electrons gives you a -1. You can see that this oxygen has a more negative charge than the oxygens on the other molecule. Okay, so 6 minus half of 2. Okay, so the -1 charge on the left oxygen means that it is less stable than a 0 formal charge element. Now we'll do the carbon. Carbon naturally has 4 valence electrons. Okay, then you have no lone pairs on the carbon. And then half of the bonding electrons, there's 8 bonding electrons for the carbon, so you take half of those, you get 0. Now we look at the oxygen on the right. Okay, it has 6 valence electrons in its natural state. You subtract the 2 lone pair electrons over on the right and half of the 6 bonding electrons, and you get a formal charge of +1. So 6 minus the 2 lone pair electrons minus half of the 6 bonding electrons gives you +1. So we see now that the oxygen on the right has a formal charge that's not 0. It has a -1, a 0, and a +1. The formal charges must add up to the charge on the molecule, which is 0. That's good. That means you did your math correctly. But you can see this is less stable. So both oxygen atoms have a charge. This makes the molecule on the right less stable than the molecule on the left. So this configuration of CO2 is the one preferred by nature and the one created in nature. Okay, let's take another example. If a molecule has a charge, the sum of the formal charges must total the charge on the molecule, in this case a -1. So for NCS minus, all formal charges must add to -1. So let's move through this one a little quicker. So nitrogen has 5 valence electrons in its natural state. It has 2 lone pair electrons here, and it has 6 bonding electrons. That's what the 3 lines mean, and you take half of those. So it's half of 6, that equals 0. Now we'll look at the carbon, and it's 4 in its natural state, no lone pairs there on the carbon, and half of the 8 bonding electrons. You add those up, you get 0. Sulfur has 6 valence electrons in its natural state, minus the 6 lone pair electrons you see there, and half of the bonding, which is half of 2, and that equals -1. Now in the middle, that nitrogen is 5 minus 6 lone pairs minus half of the 2 bonding electrons is -2. Carbon is 4 minus 0 minus half of 8, that's 0. Okay. And sulfur is 6 in its natural state minus 2 lone pair minus half of 6 is +1. The last one is 5 minus 4 lone pair minus half of the 4 bonding electrons is -1. Okay, carbon is 4 minus 0 minus half of 8 is 0. And finally, sulfur is 6 minus the 4 lone pair minus half of the 4 bonding electrons is 0. So if we look at that, we notice that all the formal charges add up to -1. But which one is the most preferred? Well, clearly it's not the one in the middle. That has the most variance from 0. It has a -2 and a -1. It's not going to be that one. It's between the first one and the third one. So how do you know which one it is? Is it the one with the -1 on the sulfur or the one with the -1 on the nitrogen? So a rule exists that if 2 formal charges are equal, below the first and third diagrams both have a formal charge of 1-. In this case, the preferred structure is the one with the negative charge on the most electronegative element. So if you look at your periodic table of electronegativities, the third structure is preferred because the negative charge is on nitrogen, which is more electronegative than sulfur. Now, a resonance structure is an alternate construction of a molecule. Ozone has a formula O3. Ozone contains 3 oxygen atoms. The central atom is connected to one of the terminal atoms with a single bond and with the other with a double bond. So you can see both of these diagrams are identical except they're flipped over. One has a double bond on the left, one has the double bond on the right. So since the double bond could be connected to either the right oxygen atom or the left oxygen atom, it can be shown in both configurations below. So that's called a resonance structure. It's 2 different configurations that are equally valid of the same molecule, and this is the way you would show a resonance structure, by drawing both of those configurations and putting a double arrow in between it. Another way of diagramming it is like this. A resonance structure is an alternate construction of a molecule. In nature, however, the second pair of electrons in the double bond is moving throughout the molecule, similar to electrons in a metallic bond. They are said to be delocalized. Ozone can be thought of as having 2 1.5 bonds, represented by the solid and dashed lines. So instead of thinking of double bond on one side, single bond on the other, you can think of it as the average of those two 1.5 bonds. And that's another way to draw a resonance structure. All right, so that takes care of this lesson on formal charge and resonance structure, and you'll be getting practice on these on the assignment.